Okay guys, what I'm going to do is video a little demonstration of things we don't normally do. So I'm going to look at how we can find the magnetic field around different shape coils, or rather see how much it varies. So I'm not going to use a Hall probe which will give me the actual value, so I'm actually going to just do relative values compared to each other. And the way I'm going to do it is I'm going to use basically an alternating field. So rather than a DC, put a Hall probe and measure the voltage as the electrons get pushed to the side of the slice. What I'm actually going to do is I'm going to measure the voltage induced in a pickup coil. Okay, so I've got here a little coil, a search coil, to find out what's going on, and as long as the field is changing through there, I'll be able to pick it up. Now, to make it more sensitive, I've got a few coils on, so it is 5,000 turns, 5,000 loops on that flat coil, and I'm going to try some different magnetic shaped producers so that we can actually find out what things are going on. So I've got a flat coil here, 320 turns, thin, quite large diameter. Okay, so two connections are here coming out from the two ends, so I'm just going to simply connect that, here we go, into a single loop, and I'm going to put an ammeter on it so we can see the effective current as well. So if I turn that on, full scale deflection 1 amp, so if that's 1 amp then that is, just tweak that a little bit, that's going to be 0.3 amps, so 0.30, I'll write that down, and I'll just take some readings which we'll record at the end. So basically I've got a transformer. Here is my primary coil producing my magnetic field. The magnetic field is changing. I can put my secondary coil at different places and you can see numbers are changing on the screen. So if I put it as close as I can get to the center, then what I'm getting, just there we go, pretty much 0.100, so a tenth of a volt on the scale here. It is normal volts, not millivolts or anything like that. Now if I take that and then I move that halfway to the coil, what you can see is I've actually managed to slightly increase the strength of the field. So instead of 0.100 I got 0.114. And if I put it at R, well, that's going to drop right off. But if I turn it sideways, oops, excuse me, I'll put it on that edge there instead. Again, I'm getting a fairly strong value. And the reason is my magnetic field is coming out of the center and curling around. So actually, if I get closer to this, I'm going to get a stronger field coming up through. The closer I get to the center, well, this one gets weaker, but then the other one gets stronger. So as I move it across to the other side, again it gets value. So it's actually lowest in the middle, it's highest near to the two sides. Now, the other more important thing for this, if I just take that to that point, so 0.13, I'll just make a note of that. If I raise it up, so if I move it up by the same as the radius, okay, the field is coming up through the centre but curling outwards, you can see it's actually dropped off a large amount. So if I make it the height R, so roughly one radius up, I'm going to take it from there, so that's about there, then I'm only going to get around about 0.04, 0.040, okay, and if I go up the same distance again, I'm going much weaker, so 0.15, 0.015. So going up further, 0.06, so it's really cutting off. So approximate values, but I'll get the same effect if I'm not over the center. So if I move it around, you'll notice it doesn't change much. If I go up to around about the radius, I'm still getting a fair bit of variation, okay, but I'm also getting variation on the outside of the coil. So again, back down to the height of the coil. If I move it to pick up any on the outside, again, it's much weaker. So just remind you, at the edge here is 0.13, as in 130. It's now 0.25-ish, and it doesn't need to go out to become very, very weak at all. So, field on this coil, the field on this coil weakens hugely as you get further and further away. Still, if it's about radius apart, so it's about that distance above, it's actually not bad. And this is actually part of a pair. So we use these on the teletron tube where we're firing electrons to make up what's called Helmholtz coils. So the distance between them is equal to the radius, and what we'll find is, if we get back up to our data, where we were moving across at the level of the coil, what we were finding is it was fairly uniform. Okay, and if we put two together, the effect of both of them, that fixed distance, so the radius distance apart, what you'll find is you get a really nice uniform field in the middle. Pretty uniform field. Almost forgot. So let's have the effect of the current. So I'll put that back, and again we're getting about 0.100, 0.99. If I turn my current up to be twice as big, I've got to be careful I don't melt what's going on here. So if I go up to 0.6 amps, there we go, then we're getting twice as much, and you can do readings all the way through, it will get exactly the same. So 0.130 was before, 0.260, so you will get exactly twice as much EMF being induced in here, therefore we're getting twice as much flux density, i.e. twice as much flux being produced. So current is proportional to turns. I'll just turn that back down before it gets warm. Okay, so we'll go through 0.3. Marvellous. Okay, so here we've got a solenoid. Looks a bit like Slinky, but that's the whole point. A solenoid that we can adjust. So what I've got clipped on is 25 loops. So counting along from 0, 1, 2, 3, 4, 5, we get up to 25 here. Now the spacing at the moment is 25 loops on 60 centimeters. Okay, let's change that. So 60 centimeters, then we'll go to 30, then we'll go to 15. Okay, and we'll see what the effect is. But first things first, go from our background reading. So we've got 0.03 volts just generally. If I hold it outside, the coils going that way means the field will go through the middle and come round. So I'm holding the orientation right. That will give me no reading. That will give me a reading. It's very small. But if I put it in the middle, we're starting to see an effect. And wherever abouts I put it in the middle, it doesn't matter. So in the middle of a solenoid is quite a uniform field all the way along. If I put it there, I should get the same reading no matter where I've put it. Okay, so that's the key thing. So in terms of the equation, what it's telling you is about the number of coils per meter. So I've got 25 coils, 25 loops, sorry, in my coil, in my long solenoid coil, and I've got 60 centimeters, and that, as I say, is giving me a reading of 0.007 volts. Okay. If we swap that, slide that in, unfortunately the reading is going to change all the way along, so we're going to keep that there. I'm going to move that into my 30 centimeter mark. I have to squash it up a little bit. There we go. But it's changing at that end as well, so that's now right. So what I've got, the same number of coils but half the length, so I have doubled the density, double the number of coils per meter. And if I put the reading in there, you can see the reading is much bigger. Now the numbers are very low, so it probably will not follow the mathematical pattern, but again, wherever I slot that in, I'm getting 0.11. Okay, a little bit of difference there, variation, but not a great deal. So 0.011. That's not very neat. So if I change that down to make the length even smaller, I'm going to struggle a little bit to actually get the surge coil into it, but we'll give that a go. So if we slide it around, there we go, and we're going to double it again. Okay. What we could do is, of course, do it as 20 centimeters. That would only be, there we go. Let's do 20. So that will not double it again. That will be 3 times the density of the original reading. So if we do that one as well, we can get more readings out of it. Again, simple ratio. So this is 3 times more dense than the original one. Again, notice that background counts there all the time. And the reading's about evenly spaced, the loops are, so 0.18. And again, you can start to see why we need a really tightly wound coil to give us a nice strong magnetic field. And if we take that to 15, that's less than 15, there we go. A little bit squashed up there in our setup. Let's just try and flatten that out a bit, because I haven't got much room to work on at the desk here. That's a little better. So if I can even that up, that's giving 15 centimeters. Again, it's not even, so if I slided it in at the bottom, you might get a different reading to at the top. Yeah, so they are less dense at the bottom, more dense at the top. I'm getting more voltage being induced at the top. I'm getting a strong magnetic field up here. So let's go again to the center, take the average, 0.021. So, okay, again we can use the mathematics of it. If I put that in, B equals mu N over L times by I. Again, if I change the current, excuse me a second. So if I just slide that into the middle, as I say, if I can get it in because the spacing is so big, so around about 0.21 in the center point. If I halve the current, then again I'm going to, oops, excuse me, that's not half the current. If I halve the current, I will get about half the result. Okay, so yeah, again with this background reading, because there's magnetism everywhere, and they'll always get a bit of voltage from the battery in here. So if you put the results in, what we can do is link in the idea of induction, where is in our induction coil, our EMF is rate of change of N phi by T, or with respect to T, which of course I can change to be A. Okay, so that's our area of our search coil, our secondary coil. That's our magnetic field strength that comes from this. Our number of coils in this setup, let me neaten that up a bit. So for this one, as I said, it is 5,000 coils in our search coil here, 5,000 turns, 5,000 loops. So we can see that the voltage being induced is proportional, as I haven't changed the time, to just B. I haven't changed N, I haven't changed A, the area of that coil. I certainly haven't changed the frequency, it's 50 Hertz, so I haven't changed that. So all I'm saying is that EMF is proportional to B. So you can do some maths with that. You can practice. The equation for the flat coil is there. We won't do a single wire because it is just so low sensitivity, it won't pick it up. And again, you can have a think about how that works. We've got a bit of background stuff. Right, we'll leave it at there. A useful little thing to see how much the density changes the strength of the magnetic field, even though we're not changing the current. Okay, we're not changing the number of lines, we're just cramming the coils together, so we cram the lines together, give us a bigger flux density. Up here, very much why we don't use flat coils if at all possible, because it changes so much, but in a solenoid, nice and even. Okay guys, I'll leave you with those data. Thank you very much.